Hello, in this session we will discuss about differential and integrated form of rate expression. Last session we discussed about rate laws. Rate laws are nothing but they are the differential expressions, and when we integrate those differential expressions we get integrated form of rate expression. Now what is integrated form of rate expression? Integrated form of rate expression explains about the time evolution of reactant and product concentration. For many elementary reaction, analytical solution is possible, that is we can evaluate the integrated form of rate expression for elementary reactions, but when the reaction get complex or when there is a complexity appears in the reaction, then analytic solution is not possible for the integration. Rather we have to take help of numerical methods. So we'll discuss only few elementary reactions. We'll start with zero order reaction. What happens in a zero order reaction? In a zero order reaction, the rate as the reaction proceeds, the rate of the reaction is independent of the concentration of the reactants, means the rate is independent of the concentration of the reactants. So on which the rate essentially depends? The rate can be dependent upon many other factors, such as if there is a catalyst present, or if it is a photochemical reaction, then the rate may be depending upon the intensity of light absorbed in such photochemical reactions. So I'll mention my general reaction. Reaction is A gives rise to product, A is the reactant and gives rise to product P, and the rate constant is K0. K0 is rate constant for zero order reaction. So if I write the rate law expression, what I'll write? I'll be writing rate is equal to K0 concentration of A raised to the power 0. Since it is a zero order reaction, that's why I have to raise the concentration to 0. So in form of differential expression, I can also write minus dA over dt and dP over dt. As the reactant concentration is decreasing, that's why there is a negative sign, and as the reactant product concentration is increasing, that's why there is a positive sign. So mathematically both the forms, both the expressions, rate law expressions are same. So I can also write minus dA over dt is equal to K0. This a to the power 0 is 1, so I can write minus dA over dt is equal to K0. If I rearrange according to their if I rearrange, I will get minus dA is equal to K0 dt. Now if I'll integrate, I'll get the integrated form of rate expression. Now the limits of integration will be A0, because A is going to product P. So the starting A0 is the starting initial concentration of the reactant, and after some time the reactant is A. After some time the reactant is A, and the time starts from 0 to any time t. So my integration limits will be A0 to A, and time limits will be T0 to T. So if I do that, I'll get A0 minus A is equal to K0 T. If I rearrange again, I can get an expression like equation 1, which says what is the rate constant for zero order reaction. Now we'll discuss first order reactions. In first order reaction, the rate will depend upon the concentration of the reactants, but the order of dependence will be one order of dependence, means the order will be 1. So corresponding rate law expression can be R is equal to K1A. Here the order is 1. Now what is K1? K1 is the rate constant for the reaction. Now I can also write the rate law in form of differential expression. So in that expression, what I'll be able to write, I can write R is equal to minus dA over dt. Here also I can write R is equal to dP over dt, because in form of product formation I can also write dP over dt. Now if I equate both the rate law expressions, what I'll get, dA over dt is equal to minus Ka. And if I rearrange the variables, I'll take dt to RHS and A to LHS. I'll get dA over A is equal to minus K1 dt. Now this is the differential rate expression. I'll integrate this one to get the integrated form of rate expression. So I'll integrate equation 2. Again my integration limit will be A0 to A, and the time limits will be t is equal to 0 to any time t. So if I do that, I'll get ln A over A0 is equal to K1 t. Now if I rearrange those things, I can get A is equal to A0 e to the power minus K1t. This is equation 3. Also I can write ln A is equal to ln A0 minus K1t. Now we'll try to understand this equation 3 in a detailed manner. What is the first expression? A is equal to A0 e to the power minus K1t. That means what is A? A is my reactant concentration after some time. and A0 is reactant concentration at the initial phase of reaction. That means for a first order reaction, the concentration of the reactant is decreasing exponentially. As the time increases, the concentration of the reactant decreases exponentially. That is one observation. Second observation will draw from the second expression of equation 3. What it says, ln A is equal to ln A0 minus K1T. We'll assume that this is in form of a straight line expression, straight line equation, y is equal to mx plus c. So what will be my y here? My y will be ln A, and mx means this minus k1t. So if I draw a plot of ln A and time, ln A in y-axis and time in x-axis, I'll get a negative slope with K1. What is K1? K1 is the rate constant for the first order reaction. So I'll get a negative slope with K1, and the y-intercept will be ln A0. So these are two important things that we can derive from the equation 3 or the first order rate expression. Also I can write K1 in form of logarithm form, and that is 1 over t 2.303 log A0 over A. So we'll be using this expression, these expressions frequently in all the next coming sessions. So again, as I said, the graphical method, if I draw a graph of like a ln concentration of the reactant and time, I'll get the concentration of reactant decreases with time for first order according to equation 3. So for how the decrease will, it decreases exponentially. Now what is the extent of decrease, what is the extent of exponential decrease? That depends upon the rate constant, the K1. So when the rate constant is more, the exponential decrease is more heavier, and when the rate constant is less, the exponential decrease is not that much heavier. Similarly, if I want to draw a linear graph, I have to take logarithm of this corresponding graph. Again, here also, as the rate constant increases, the rate of decrease of product reactant concentration is faster compared to the case when the rate constant is higher. We'll take some of the examples of first order decomposition or first order reaction example. We'll discuss decomposition of nitrous oxide. When nitrous oxide decomposes to form nitrogen gas and oxygen gas, it follows first order reaction. So we have to monitor its concentration, but here in this particular example we cannot monitor concentration because it is a gaseous substance. Rather, we'll measure the partial pressures of the corresponding gases. So reactant and products are gases, so instead of measuring the concentration, we'll directly monitor the partial pressure, and that is easy to monitor. Suppose at the zero time or at the starting of the reaction, the partial pressure was Pi for nitrous oxide, and for nitrogen gas and oxygen gas there was no initial concentration, so partial pressure is 0. After some time, the partial pressure of nitrous oxide has reduced to Pi minus x, and x amount of, or x is the pressure that is created by nitrogen gas and oxygen gas. So what will be total pressure? Total pressure will be partial pressure of nitrous oxide, total partial pressure of nitrogen gas, and partial pressure of oxygen gas after some time t. So if I do that, if I add up all the partial pressures, what I'll get? Pi plus x by 2. So why I am doing this? So from this expression I can find out x in terms of P and Pi. What is P? Total pressure, and Pi is initial pressure of nitrous oxide at zero time. And what is P? Total pressure of all the gases after some time t. So my aim is to find out x in form of P and Pi. So I can do that. Now what is partial pressure of nitrous oxide after time t? It is Pi minus x. So then I'll substitute the value for x, then I'll get that partial pressure of nitrous oxide is 3 Pi minus 2P. Now I'll use the first order rate expression. The first order rate constant expression is 1 over T ln, the numerator was initial concentration divided by concentration after some time t. So initial concentration, instead of initial concentration, we'll take initial partial pressure, and instead of concentration after some time t, we'll take partial pressure of nitrous oxide after some time t. So what is partial pressure of nitrous oxide after some time t of the reaction? 3pi minus 2p. So if I substitute that, I'll get a rate expression like this K1. Now there is another example, common example which follows first order kinetics, that is acid hydrolysis of ethyl acetate. Ethyl acetate gets hydrolyzed in presence of by acid catalyst to form acetic acid and ethyl alcohol. Now how to monitor this reaction, or how to observe the change in concentration of reactant? What is the reactant? Ethyl acetate. We will do that. Generally it is done in an indirect method. We monitor the concentration of this catalyst, that is the acid catalyst. And how do we do that? We generally titrate this acid catalyst using a base. So suppose V infinite is alkali used at the end of the process and V0 is alkali used initially, then V infinity minus V0 will give us total amount of the acid consumed during this process. And similarly, V infinity minus Vt will give us the amount of acid consumed at any time of the reaction. So if I put these expressions, I'll get my rate constant for this particular reaction is 1 over T ln V infinity minus V0 over V infinity minus Vt. Then we'll discuss something called half-life period. It is the time required when the initial reactant gets decreased to 50% of its value. Means reactant, suppose we started with 100 gram, when it becomes 50 gram, what is the time taken? That time is called half-life period. So it is denoted by T half. So at T half, what will happen? My reactant concentration will be A0 over 2, means it is the reactant concentration at the starting stage divided by half. So if I substitute this expression in the equation 3, what was equation 3? Equation 3 was the rate expression for first order reaction. So instead of time, I will substitute T half, and K1 is the first order rate constant ln A0 over A. What was A? What is A for half-life period? A is A0 over 2. So if I do that, if I rearrange, I will get ln 2, and ln 2 means 0.693. ln 2 value is 0.693. So I'll get my half-life time as 0.693 over K1. So it is important to note half-life period of a first order reaction is independent of initial concentration of reactant, and it only depends upon the rate constant of the reaction. So half-life is 0.693 over K1, means this equation 4 is applicable to only first order reaction, and for first order reaction half-life period is independent of initial concentration of the reactant. And then one more concept we will discuss, that is called time constant. It is the time required when the reactant concentration decreases to 1 by eth of its initial value, means A will be A0 over E. So I'll put that this condition in my rate expression condition, that is equation 3. So K1, instead of time, I am writing time constant tau is equal to ln A0 over A. A will be A0 over E because it is decreasing A by eth time. So I'll be getting ln E, which is equal to 1. And so what is my time constant expression? Time constant is equal to 1 over K1. So I can say, therefore we can say that time constant of a first order reaction is reciprocal of first order rate constant. So with this I'll stop here. Next session we will discuss integrated rate expression for second order reaction.